Last section in this unit. You guys have done it. Almost there. Just this one. And then you're done with the unit. I know it's a big one. It's 7. And you can imagine this unit was connected with Newton's laws, so it would have been even longer if I didn't split them apart. So inclines. We are going to learn what are inclines. We're going to figure some stuff out with that and then solve problems. Let's figure out what an incline is. So if you can imagine a ball sitting on a level surface, it might look something like this. If we were to look at forces, you've got Fg down, normal force up. Okay, these are balanced. So since these are balanced, you're not going to accelerate. So the ball on a surface does not move, it just sits there. Now, if I were to place this ball onto an inclined plane, it just means a slanted surface like this. What's going to happen? Well, clearly the ball's going to roll down the hill, but I'm not applying a force to it. It's actually gravity that's going to pull it down. So we need to look at how does the normal force change? How does force of gravity change once I take something from level and incline it? So let's take a look at the forces. So we've got Fg. Fg is always going to pull straight down. Force of gravity always pulls towards the center of the earth. However, normal force is always perpendicular. So as I showed you before, if I have a flat surface, as soon as I rotate this, my normal force changes because it has to be 90 degrees to the surface. So between the surface here, this has to be 90 degrees. So this, as I rotate along, is going to change. That gives us a normal force that is no longer straight up. Now it's slanted because my surface is slanted. So in order to solve problems for inclines, the very first thing we need to do is break Fg into 2 components. Now you might be thinking, but Fg is straight down. How can we break that into x and y? It's only a y component. That's kinematics. Inclines breaks the rules a little bit in that we have a different coordinate system. So instead, what we have for this is we're going to have Fg parallel. So parallel meaning parallel to the surface. If you look at the Fg parallel arrow and the surface, those are side by side. This is parallel. They're moving along each other. So if we're dealing with the parallel component, we also have perpendicular. So perpendicular means 90 degrees to something. You see with Fg perpendicular, the sign for perpendicular is a upside down T. You see a 90-degree angle there. So between the surface, the incline, and Fg parallel is 90 degrees. That means those are perpendicular. So in the question, your angle is always going to be given as the bottom of the incline. According to the diagram here with Fg, Fg parallel, Fg perpendicular, your angle is going to be here. So depending on how you draw your lines, theta is always going to be beside your perpendicular. That's always going to be the case because I won't give you the angle at the top of the triangle, always the one at the bottom. So you just need to remember that that's the case there. I can explain more to you in person if you want to know why. But I'm not going to get into that here. So if we expand this out and just take a look at Fg and its 2 components, because we need to figure out how do I actually solve for parallel and perpendicular. Once I have that, the rest of the work is pretty straightforward. This is the part that you really need to understand to be able to get the rest of this section. This is a right triangle. So if I look at sine theta, which remember is equal to opposite over hypotenuse, my opposite of the angle is Fg parallel. My hypotenuse is Fg. So we have sine theta equals Fg parallel over Fg. And if I multiply Fg onto the other side, I get that Fg parallel is equal to force of gravity times sine theta. So now it's just dependent on what theta is. And we can do the same thing for perpendicular, except for perpendicular, we're dealing with cosine because we're dealing with the adjacent side. And that's equal to Fg perpendicular over Fg, which is the hypotenuse, and then solve for Fg perpendicular. So you need to be comfortable with Fg parallel being Fg sine theta and Fg perpendicular being Fg cos theta. So there's 2 important things to notice here. 1, the parallel component, that's the only part that pulls down the ramp. And the perpendicular component is equal to an opposite Fn. So if I'm ever looking for normal force, it's equal to the perpendicular. And Fg parallel is what's causing our ball to roll down the ramp or the box to roll down the ramp or whatever's on the ramp. Those are important things to note. With this bit of information, we can now solve problems with inclines. So first example here, we've got a 5 kilogram block sliding down a plane. We want to know acceleration. So looking at the forces on this, I'm going to show you it multiple times. I'm sorry it might get boring, but I want to get you comfortable with seeing what the forces look like. So FG, always straight down, normal force at an angle, break up FG into parallel and perpendicular. And remember, the angle is here with FG perpendicular. So remember, the normal force and FG perpendicular cancel each other out. So our acceleration is caused by FG parallel. So F net equals FG parallel. F net is MA. FG parallel, I just showed you in the other slide how we got this. Plug in numbers, solve for acceleration. So another question, how much force would be required to push a 25 kilogram object up an incline? And notice here it's frictionless, because that's important. It's constant velocity, so let's take a look at the forces. Fg straight down, Fn perpendicular to the surface. And then we've got the parallel and perpendicular components of Fg, where the angle is at the bottom. Hopefully that diagram's starting to sink in a little bit and you're getting comfortable with that on an incline. There's no friction, but in this case we're pushing this block up the incline. So I must have a force applied going up the incline. And if we're moving at constant velocity, we know that the applied force is equal to Fg parallel. That must be the case. So if I'm solving for force applied, we know what Fg parallel is equal to. Plug in numbers, solve for applied force. There you go. So again, drawing the diagram might be the hardest part, but once you get that, the equation's not too bad. Example 3, we've got a 42 kilogram block sliding down an inclined plane. Now we have friction. So let's look at the forces. Hopefully by now you can draw this before I even say it. Fg straight down, normal force is perpendicular to the surface, break up Fg into parallel, perpendicular, put the angle. Okay? Same thing. Notice that hasn't changed in any of these questions. So hopefully you got this. Now, it's sliding down the incline. We're looking for acceleration and we have friction. So we need to make sure we put friction into this equation. So F net is equal to the winning force, Fg parallel, minus force of friction, which is the losing force. Now, here's where it gets a little bit tricky with the friction force. Remember, friction is equal to mu Fn. And typically, Fn is equal to mass times g. But in this case, the normal force is not equal to Fg. It's actually equal to the perpendicular component. So I need to deal with a Fg perpendicular to solve this. I've shown you what that looks like. That shouldn't be a surprise. Now we need to take this and put it into our equation. So the equation looks gross, but these two things, Fg parallel and Fg perpendicular, you've seen those. That's why I started with that. Now we can plug in numbers. We have all those numbers. It's a big, long equation. I can simplify this because everything on the right-hand side of the equation is a number. So you can just plug that into the calculator and get a number and solve for A. Now I want to point something out with this. This is more an extension thing. It might not apply to all of you, but you might have noticed right after the F net equation where we had m times a equals the whole rest of the equation, notice that I have a mass in each of these terms. So I could technically have canceled out the mass. So there might be a situation where you're given a question where there is no mass. It just says a block slides down an incline. And you can actually solve this without needing the mass because they all end up canceling out. So if you ever are given a case where there's no mass, they will cancel out. And you just need to make the equation and mass will cancel out. There you go. We're done with the inclines. We're done with the unit. Tension, inclines, those are definitely the two you need to focus at. Those are the harder sections. And making sure you know how to make F-net equations. Those are all really essential for this unit. All right, Girly, do you think by now people have figured out who you are?
I think so.
You think so? This is the 7th thingy that we did. You want to introduce yourself?
Hi, my name starts with the A.
And it starts with an A.
And ends with the
And also ends with an A. Are there some letters in between?
Yes.
Or is it just ah?
No, it has 3 letters in between.
3 letters in between. Okay, perfect. Well, this is going to be our last clip that we're going to record together, Girly. Are you sad about this?
No.
Okay, perfect. So this one's from Tangled, which is a story all about Rapunzel. And you know about Rapunzel?
Yep.
Because you played Rapunzel. You're reading at school, right?
Yes.
Perfect. So you know what's going to happen?
Yeah.
Okay. So let's watch this and see what you think doesn't work.
Okay.
Okay, what do you think with this little lady?
I don't think that she can pull up
Why?
because her hair is not that strong.
Her hair's not that strong. You think the hair would break?
Yes.
Ah, okay.
The hair would fall down.
Mm-hmm. Anything else? No, just
No.
that. Do you think she's strong enough to pull her up?
Nope.
That'd be pretty hard, right?
Yeah.
Even though her hair is over the loop, so it's like a pulley system. Do you know what a pulley is?
Yeah.
It makes it so that you have to apply less force
Yeah.
to pull it up. That's what a pulley system is. But I think that would be pretty hard. Do you think you could pull someone up like this? If
No.
you had your hair, you
No.
loop it over the thingy and then
No.
pull someone up? How do you think that would feel on your hair?
Ouchies.
Yep. Although she's got lots of hair, she's not really pulling it off of her head.
I would feel scared
To go up on the hair
Yeah.
or to lift?
to get lifted up.
Mm-hmm. That would be pretty scary. She would have to be really, really strong to lift up a full adult.
Yeah.
Can you carry me right now?
No.
No. Do you think you could pull me up?
No.
Okay. So there's that one. Do you want to say bye to everyone because this is the last time you'll be on a video?
Yeah.
Okay.
Bye.
Bye.
Bye.